Okay, it's time to talk about reactions of alkenes. We already said these are addition reactions. Why? Because the double bond is the functional group of the alkenes of these compounds. So any reaction happening will happen on the double bond. So addition can be from one side of the molecule, means X and Y, can be any random atoms, can be added from one side of molecule. Such an addition is called syn addition. Learn it now. Syn addition means addition is from one side of the molecule, because these molecules have a double bond. When the two atoms are added from the same side, we call it syn addition. By adding the two atoms, double bond changes to single bond to keep the octet of these two carbons. Or these two atoms can be added from two opposite sides, and we call it anti-addition. So keep it in mind that addition to double bond can be done either syn or anti. We are going to work on 5 types of reactions. You have them on page 7. You have them in this chapter. Addition of HX. X is fluorine, chlorine, bromine, and iodine, mainly chlorine, bromine, and iodine. Addition of water, addition of halogen, and addition of water in a different way. I will start talking about all of these in details, and also addition of OH and halogen. So I will start working from addition of hydrogen halide. We will talk about each one in detail, and you will learn more facts about each of them. So let's start with electrophilic addition of HX, hydrogen halide. So let's work with the same example that we have here. Seems like I need to change my markers. Let's say we have this molecule, this alkene. So if you want to add HCl, HCl is a hydrogen halide, right? X here is Cl. If we want to add HCl, we are adding a hydrogen atom and a chlorine atom. So we have two ways. Hydrogen can stick to this carbon and chlorine to this carbon, and vice versa, right? So let's draw them. Let's say we are not talking about the anti and syn here. Let's just focus on the type of addition. So let's say we have CH3, these two, and we said the first compound form, the first product, let's have Cl here, plus already 2 hydrogens on this carbon. The third hydrogen comes and sticks. Another product is that hydrogen attaches to this carbon and chlorine to this carbon. So you have CH3 and CH3. You had them already in your original molecule. Then you have hydrogen, and you have hydrogen, hydrogen, and chlorine. Okay? Now, the argument here is that we have the experiments shown that this is the major product. major product. Now we have to get familiar with a rule. It's called Markovnikov's rule. Markovnikov's rule. A Russian scientist who worked on these types of reactions and output the rule. According to Markovnikov's rule, in addition to double bonds, hydrogen will be added to carbon with more hydrogen. So basically, we say it's a hydrogen-rich carbon, and this is the hydrogen-poor carbon, right? So basically, hydrogen attaches to carbon with more hydrogen, rich gets richer. So hydrogen attaches to hydrogen-rich carbon. That's what happened here, right? So before we get to the mechanism of this reaction to find out why such a thing happens, let's work on some examples, and then we will open this to its mechanism to learn what is really happening in this type of reaction. Why? Major product is the one with more hydrogens on one carbon. Let's work on this. And you need to add some ether to make it more soluble. So, no matter how big the molecule is, you just need to focus on the double bond, because this is the function group and this is the sensitive part of the molecule that reacts. So, now let's determine which carbon has more hydrogen, or let's determine if the carbons are different as far as the number of hydrogens. Seems like this carbon already has its 4 bonds. How about this carbon, the other one involved in double bond? We have 1, 2, 3, and it has the 4th bond is a hydrogen. So this is our hydrogen-rich carbon, right? According to Markovnikov's rule, hydrogen attaches to this carbon and bromine to this carbon. So that the final product is CH3. What did we say is going to attach? That was the hydrogen poor carbon. So bromine attaches, and you can draw the hydrogens here or just simply ignore, because it's a skeletal structure. When you don't put it, means that the hydrogens are automatically attached there. So this is going to be your major product, or let's say the sole product, like the percentage of this product is so much more than the other one. Let's work on another example to show what we mean by applying Markovnikov rule. Again, we are going to add HBr to an alkene. Now look, we are going to determine if the hydrogens, if the carbons are different as far as the number of hydrogens. Seems like there is 1 hydrogen attached to this carbon of double bond and 1 hydrogen to this. So there is no difference between the carbons of double bond in this case. So we will end up having 2 products. Hydrogen attached to here, bromine here, or hydrogen here and bromine here. Because there is no point to apply Markovnikov rule, each of the carbons of double bond have 1 hydrogen, so there is a mixture of product formed. CH2, CH3, 1 hydrogen already, another hydrogen, CH3, hydrogen, and bromine. Also, we have CH2, CH3. Let's put bromine here this time. CH3. 2 hydrogens. So you see, if there is no difference between the carbons as far as the number of hydrogens on them, we have 2 products, a mixture of products. If there is a difference, then we need to apply Markovnikov rule. Now, I promised you to work on the mechanism of this reaction to find out why we have the Markovnikov rule on these types of reaction. Mechanism of addition of HX to alkenes. So let's work on just a random alkene. Let's just see how the mechanism is. This is the first mechanism that you need to know. Mechanism shows the steps of each reaction in details. Basically, they tell the story of the reaction. And in the reactions, in the mechanisms, we work with the arrows, with the electrons, and we need to be very detailed and make sure that we know how to draw the arrows. So what happens here is that this hydrogen and bromine are involved in a polar bond. So hydrogen is partially positive and bromine is partially negative. This double bond is a nucleophile, is full of electrons. So attack is always from nucleophile towards electrophile. Hydrogen cannot tolerate more than one bond, so this bond breaks over bromide. So step 1, you will end up having, at this point it doesn't matter, hydrogen attaches to which carbon. And if we determine the formal charge, we have a positive charge here and there is a bromide in the solution, right? So in step 2, nucleophile is bromide and we have an electrophile here. So nucleophile attacks electrophile to form the product. Alright? So in the mechanisms, we need to make sure that we start from the right nucleophile. The tip of the arrow must be on the electrophile. And for example, for bromine, you cannot just leave it in the air. No, this is not correct. The electrons move over bromine. So what is different, what is very important in the mechanism is how to draw the arrows. So one more time. In step 1, nucleophile double bond attacks the hydrogen and the hydrogen will be attached to the carbon. Bromine will detach from hydrogen and the other carbon will have a positive charge, positive formal charge. We know how to determine the formal charge. So now this carbon will act as an electrophile and the bromide or the halide, if you have iodide or chloride, this acts as nucleophile because now all the electrons are on bromide, on the halide. Then in step 2, we have a new nucleophile which is halide and an electrophile which is a positive charge on this carbon. Nucleophile attacks electrophile and attaches to it. This intermediate that we have is called carbocation. Carbocation means a cation on the carbon. You had it before. So in the middle of this reaction, a carbocation is formed. So let's work on the previous example that we had. So we apply the Markovnikov rule. You Remember we said if we add a hydrogen halide, hydrogen will attach to hydrogen-rich carbon. So let's see why. The first step, double bond attacks hydrogen and electrons remain on bromine. So we have CH3. We said hydrogen-rich carbon gets the hydrogen, right? So carbon has 3 hydrogens now. What is the positive charge? Where is the positive charge on this carbon, right? What type of carbocation is it? Primary, secondary, or tertiary? This carbon carrying the positive charge is connected to 1, 2, 3 more carbons. So it's a tertiary carbocation. Tertiary carbocation. A flashback to the stability of carbocations. Stability. Carbocations. Tertiary, more stable than secondary, more stable than primary, and the reason is because of the distribution of the charges. So we are dealing with a tertiary carbocation, which is the most stable. Now allow me to draw the other carbocation if hydrogen would attach to this carbon, to hydrogen poor carbon. So you would have CH3, a hydrogen here. Then we would say the charge remains on this carbon. Now what type of carbocation is this one? The carbon carrying positive charge is connected to only 1 more carbon, so it's primary. Now look, we have a primary carbocation comparing to the tertiary carbocation. So which one is more stable? Obviously, tertiary carbocation. So comparing to this doesn't form or very, very, very low percentage. So this is the one that continues with bromide ion. And and we have it here. And we will end up having our product. That's the meaning of Markovnikov rule. You see at the end, hydrogen-rich carbon and hydrogen-poor carbon. That's the reason. So what is the reason of applying Markovnikov rule? The creation, the formation of more stable carbocation. Okay? Let's work on one more example, on a cyclic example, on a ring. We have this cyclopentene. We add it to HCl. Let's draw the mechanism. First, the nucleophile attacks electrophile, right? Positive, negative. So this is electrophile, this is a nucleophile. So, is there any difference between the type of the hydrogens on the carbons? No, there is one hydrogen here, one hydrogen here. So, go ahead and attach hydrogen to whichever carbon you want. I'll attach it. I don't like this. Cyclopentane. So, let's add it here. Then we have a positive charge on the other one. Now you have a chloride, right? Because the charge opened, the bond opened on chlorine. Now chlorine will attack to this, or vice versa, as if like you flip the molecule. You can put the hydrogen here, you can ignore putting the hydrogen in the skeletal structure. Now, let's work on another example without the mechanism. Now we know the mechanism, now we know the Markovnikov rule. So on page 10 of your study guide, I'm working on A. What product is formed when this alkene is treated with HCl? With HCl. Okay? So this is a methyl group, right? There is a CH3 at the end of this bond. we don't show in the skeletal structure. And here we have an invisible hydrogen. So it seems like we have a hydrogen-rich carbon, hydrogen-poor carbon, right? So hydrogen must attach to this carbon, chlorine must attach to this carbon. Go ahead, remove the double bond and add your atoms. Again, you can add the hydrogens, but since this is a skeletal structure, there's no point in showing the hydrogens. All right? If you want to work on C, this is C. All right? So we add HCl. First, determine the type of carbons. This carbon has 2 hydrogens, and this carbon has no hydrogens. So hydrogen will attach to this carbon and chlorine will attach to this carbon. These are, by the way, these are not the mechanism. I'm just showing you how the attachment's happening. So you have 3 hydrogens and you have a chlorine and you already have a methyl group. Okay? So that's as far as this. But there's one point that you need to be careful in the addition basically into the alkenes. Let's say we have this. What is that point? The carbocation rearrangement. Carbocation rearrangement. So let's go with the mechanism together. This is the hydrogen-rich carbon. This is the hydrogen-poor carbon, correct? So seems like hydrogen will be added here, chlorine will be added here. Now, let's do it step by step. Attack is from nucleophile to electrophile, and the bond will open on chlorine. So, I will draw it here. Let's say hydrogens are going to attach to this carbon. Now we have the positive charge on this carbon, correct? Now, you might say, okay, now chlorine is going to attach here and done. But this is the, what type of carbocation? Carbon carrying positive charge is connected to 2 more carbons. So it's a secondary carbocation. It seems like after the final product has been isolated, seems like there is a shift from the carbon, the adjacent carbon from the hydrogen on it towards this carbon. So this is the carbocation rearrangement. So look what happens. CH3 remains the same, nothing happens on this. And we have 2 hydrogens here now. Okay, this is the same hydrogen. Let me just keep it color coded. And what happens here, the positive charge remains here. So hydrogen, we call it H shift or hydrogen shift. Hydrogen moves from only, not the one that just grabbed the hydrogen, the other one, the one that was not involved in double bond. There is a hydrogen available there. And our carbocation is secondary, its stability is average. So what happens is that on the adjacent carbon of carbocation, there is a hydrogen. Hydrogen shifts on that carbon with the positive charge, so positive charge shifts on the other carbon. Now tell me what type of carbocation you have. 1, 2, 3, so it's a tertiary carbocation. Look what happened. A secondary carbocation with the average stability changed to a tertiary carbocation with more stability. Tertiary carbocation is more stable than secondary. So because a less stable carbocation was able to change to a more stable carbocation, this shift that needs energy, because every bond breaking needs energy, right? This bond is worth breaking and hydrogen shifting on the other carbon to form the tertiary carbocation. Now this molecule is ready to form the final product with CH3. I'm just finishing it with CH3 here, CH2, and CCl. CH3. So your double bond was between these two, but chlorine is on the other one. Yeah, on the adjacent carbon. So seems like there is a rearrangement happening, but the rearrangement doesn't happen all the time. Only if you go from a primary or secondary to a tertiary carbocation, this shift, this rearrangement is worth doing. Otherwise, it's not going to happen because this breaking this bond needs some energy. Okay? Now, let's work on some examples before we move to the next reaction. We are supposed to draw the mechanism for this to this. So look, double bond is here. You expect bromine and hydrogen will be added to these two carbons. But what you see here, this bromine is added to the adjacent carbon. So there is a rearrangement happened here. So let's work on the mechanism. Let's see HBr. Right? This is the first step, step 1, towards the formation of carbocation. Which one grabs the hydrogen? Hydrogen-rich carbon, 2 hydrogens here and 1 hydrogen here. So hydrogen here, and there is a positive charge remaining here. What type of carbocation do you have? The carbon carrying the positive charge is connected to 2 other carbons, so it's a secondary carbocation. But if this molecule, this group, this methyl group, moves here to this carbon, rearrangement happens here. And rearrangement it always happens after the formation of carbocation. This is this, right? So positive charge remains on this carbon. You know how to calculate the formal charge. You learned it at the beginning of semester. And so we call it methyl shift. CH3 is added to the other carbon, so we call it methyl shift. Just like hydrogen shift, hydride shift, we have a methyl shift. Both hydride shift and methyl shift happen to form a more stable carbocation. So we we went from secondary carbocation to 1, 2, 3 tertiary carbocation. Now the molecule is ready to receive bromide. Isn't it the same product you're talking about? Yeah. So that's how you deal with this. Whenever you see your halogen on an unexpected spot, that's the sign for the rearrangement. All right. So now one more thing is that because these carbocations are planar molecules, like let's say we are dealing with this. This is a methyl group, this is a hydrogen here. So when we add HCl, hydrogen will be added to this carbon. Okay. Now positive charge is here. Now, chlorine, or let's because we're talking about the stereochemistry. So, here, chlorine can be added from the front of the molecule or can be added from the other side of the molecule, from the back, because it's a planar carbocation. Is the hybrid is sp2, so we can have a mix of chiral products. We can have hydrogen and chlorine be added from the same side, so it's going to be syn addition. Or chlorine can be added from the opposite side. Remember we talked about syn and anti-addition. So you will end up having two types of products as far as the stereochemistry. So if you want to work on one more example before we finish this video, we have this compound. So we're supposed to draw the products only, including the stereochemistry. So hydrogen will be added here and bromine will be added here. So we have two choices. We can have hydrogens and bromine from both sides, from the same side, syn. Let's say we're talking about this hydrogen. Okay, and we can also have anti-addition. Let's say we're still talking about this hydrogen, but this time bromine will be added from the opposite side, so it's an anti. So we have, as far as the stereochemistry for this type of reactions, we have a mixture of products, maybe mixture of chiral compounds R and S. Okay, this reaction was the key reaction to learn about the electrophilic addition to alkenes. The rest of the reactions shouldn't be that hard to explain and learn. Please practice enough until we move to the next portion.